Everyone. So today I talk about the correlation between supernova fallback and the progenitor's hydrogen envelope. My name is Kengo Shinoda from University of Tokyo, and there is co-researchers as here. So let's start. Yes. So so first I introduce you the brief core of supernova mechanism. So a massive star exceeds 8 solar masses occurs a core supernova explosion. And at the pre-supernova phase, so the progenitor forms an onion structure like this. So their hydrogen envelope and helium core contains carbon, oxygen, neon, magnesium, blah, blah, and iron core at the center. At some point, iron core collapses to the neutron star, and the shock wave generated by the collision between the falling matter and the neutron star surface. So this phase is called core bounce, and we set 0 second as the core bounce time. And after about 1 second, the shock wave propagates through the progenitor structure. And after about 10 to 3 or 6 seconds, so the shock wave breaks through the photosphere of the progenitor, and it is called the shock breakout phase. So here is one question. So how much is a compact object mass? Is it completely same as their second? So the answer is no, because there is a mass accretion of the central object from shock propagation phase to shock breakout phase. This accretion is called fallback. So this is okay. So next I talk about the effect of fallback by hydrogen envelope. So Chan et al. Calculates the time evolution of accretion rate and masses by solving hydrodynamic simulation. So they use two initial conditions. So first is a metal-free star, which have a rich hydrogen envelope. And another one is a solar metal star, which have a poor hydrogen envelope. So please look this upper panel. So x-axis is time and the vertical axis is accretion rate. So after propagation, after shock propagates in hydrogen envelope, blue line, which have a rich hydrogen envelope, has a numerous mass accretion rate, but red one does not. And red one is same to the dotted line, which is an analytic solution of free expansion. So due to this effect, so after about 10 to 4 seconds, hydrogen-rich progenitor has increasing about 2 solar masses, but hydrogen-poor red one does not. So it is the same, almost same about after 10 to 4 seconds. Okay, so to summarize this, so metal-free star has a high fallback accretion rate and higher remnant masses. But solar metal star has a fallback accretion rate, lower fallback accretion rate and lower remnant masses. So by hydrogen envelope, it may increase accretion rate, but there is some clear points. For example, so these progenitor have different helium core structure. And how is the remnant mass how remnant mass increases by hydrogen envelope structure, and what is dependence of explosion energy. So in this work, so our motivation is how does the hydrogen envelope affect fallback? And our simulation is the calculation of spherically symmetric 1D fluid dynamics in Progenitor with only different hydrogen envelope. So here is initial condition we use. So black one is hydrogen-rich Progenitor, which metallicity is 10 to minus 4 solar metallicity, and Zern's mass is 18 solar masses from the stellar evolution result of Uzuri et al. And please look at this figure, and x-axis is radius, and vertical, so solid vertical axis is density, and dotted is interior mass. So we make another initial condition from this type 2 progenitor. So this progenitor has a poor hydrogen envelope. So to make this, we remove hydrogen envelope from this type 2 progenitor by using method Matsuna et al. 1999. So by doing this, we can remove about 30 solar masses of the hydrogen envelope. So next is about setup. So we use code as Athena++, which is hydrodynamic simulation code. And we solve equation of pure hydro, adding so safe gravity term. So first is a continuity of mass, momentum, and energy. And we use EOS. Our EOS is adiabatic gamma EOS, and gamma is fixed to 5/3. And next is, so we reproduce supernova explosion using thermal bomb method. So in detail, we inject internal energy at around 10 to 7 centimeter and calculate total energy of ejector as explosion energy. So we put injection energy to reproduce explosion energy to be 10 to 48 to 52 erg. Okay, so next is the result of shock evolution, as the injection energy is 8 times 10 to 50 erg. So this is a figure of x-axis radius, and vertical axis is velocity by normalized 10 to 8 centimeter per second. And black one is type 2 progenitor, which have a rich hydrogen envelope. But so another one, red one is like type 2b progenitor, which has poor hydrogen envelope. So before shock running in envelope, this structure is almost same, but continuing time. So after running to hydrogen envelope, type 2's one is different from red one. And continue time. So another shock region appear behind the whole shock region. So this area. So we call it reverse shock. So after shock running in envelope, so this shock structure is changed. So to continue time, so this reverse shock will fall to the center. So yes, to decrease to 0 centimeter per second, and reverse shock falls to the center. Yes, so this in falling reverse shock affects accretion rate. So after before the reverse shock unfolds, these two mass accretion is almost same, but the reverse shock after reverse shock holds to the center, So black one hydrogen-rich progenitor has a numerous mass accretion rate, but red one does not. And it is same to the blue dotted line, which is which is a analytic solution of pre-expansion. So due to this effect, so hydrogen poor progenitor is almost constant from 10 to 2 times 10 to 3 seconds, but hydrogen rich progenitor as remnant mass increases about 2 solar masses. Okay, so finally, the black one hydrogen rich progenitor's remnant mass is 5.8 solar masses, and red one is 3.8 solar masses. So here is another result of strong explosion. So at this time, injection energy is 2 times 10 to 51 erg. So in this injection energy, so accretion rate is almost same at all time. So the remnant mass time evolution is almost same too. And this final remnant mass is about 1.8 solar masses. So here is the relation explosion energy and the remnant masses. So this figures x-axis is explosion energy. It is the total energy of the ejector. And vertical axis is remnant masses. And we find this steep increasing of remnant masses region. This is comes from the infalling reverse shock. And we call it transition region. And it is rigid at 2.5 solar masses to 6 solar masses. So in upper this transition region, the reverse shock enforced completely. But in lower this transition region, the reverse shock escaped from the gravity of the central compact object. Next is hydrogen poor result. It is we can find the shallow transition regions than type 2's 1. And the remnant mass is almost same at explosion energy because 4 times 10 to 50 erg, because it is no infalling the reverse shock in this region. So here is expanded result. Adding Zam's mass is 18 to 28 solar masses, but these all model has the same metallicity 10 to minus 4 solar metallicity. And this figures x-axis is explosion energy and vertical axis is remnant mass. And we find all model have transition regions. And we find that so transition region, it is corresponds to multiplied factor 2 or 3 of hydrogen, each hydrogen envelope's binding energy. Okay, it is a summary. So our simulation is calculated of spherical symmetrical 1D fluid dynamics in progenitor with only defined hydrogen envelope. And result is we find transition region, and it is corresponds to 2.5 solar masses to 6 solar masses at 80 solar masses. And transition regions corresponds to 2 or 3 times to gravitational energy of hydrogen envelope. Okay, that's all. Thank you.
Thank you, Kengo. Questions?
So what was the mass of the explosion that you showed the movie of? Was that the tire mass progenitor, or the one where you were showing the movie of the shock moving out? What was the I was just a little surprised that your velocity was only 2.5 times 10 to the 8 centimeters per second. But is it because there's a lot of mass in the in the helium core of that model?
So your question is what's enforced?
Well, okay, go back to the movie, and I guess my question is, before that dashed line, what is the mass contained in the helium core region?
Yes, in this in this case, injection energy is 8 times 10 to 50 egg. So helium core already falls, and sorry, this reverse shock contains helium core in this injection energy.
And what was your helium core mass?
Is a progenitor?
Yeah. Is it? It was like, so it's like a 6 solar mass helium core. Okay. I'm a little surprised that with 6 solar mass of helium and 8 times 10 to the 50 erg explosion, the velocity, peak velocity is only 2.5 times 10 to the 8 centimeters per second.
Okay, so this figure is suitable for your question. So this is explosion energy and remnant masses and fallings mass coordinate of each layer. So injection energy is when injection energy is 8 times 10 to 50 egg, it is corresponding to the probably here, and probably the reverse shock contains helium layer. So is it suitable for you?
Further questions? Yeah.
Thank you. This is very interesting. I wanted to emphasize one of the limitations that you brought up, that there is this issue of the explosion energy dependence.
Yeah.
And the comparison you do here is that for the same explosion energy, you look at solar metallicity and the zero metallicity. However, the metallicity itself, depending on how the mass loss occurs, can be correlated with the core compactness, because there's a correlation between the hydrogen and the helium envelope and the core compactness. And the core compactness can be correlated with the explosion energy. So different metallicities can leave behind different explosion energies, with higher metallicities perhaps leaving behind weaker explosion energies, because you would have more mass unbinding, you'd have a lower compactness. And so there's a little bit more nuance here. And you really can't do a comparison for the same explosion energy, but for different metallicities.
So
but this is still this is the first step to do, but that's an important detail, I think.
Sorry, so
if you change the metallicity, you'll change the explosion energy. That's my point. If you change the metallicity, you will change the explosion energy.
Okay. So if we change metallicity, for example, solar metallicity, this transition area is lower explosion energy, because solar metallicity progenitor has a tiny hydrogen envelope binding energy, so approximately 10 to 48 egg. But this progenitor has a big binding energy of hydrogen envelope, approximately 10 to 50 egg. So this this transition region positioning as about 10 to 50 egg. But in solar metallicity, it will come to 10 to 48 egg. So is it okay?
Thank you.
Thank you.
Thanks, David. And if there are no further questions, let's thank Kengo again.